Good afternoon, dear students, and welcome back to our course. In the last lecture, we discussed in detail about the concept of error signal and how to calculate the value of steady state error. So, first we have taken a closed loop control system where our objective is to find a mathematical expression to determine the value of error signal. So, equation number one indicate the mathematical expression to calculate the value of error signal, and according to equation number 1, error signal is given as r of s divided by 1 plus g of s into h of s, where this r of s indicate Laplace transform of input. And based on our previous discussion, we know that we have four different types of standard test input signal. Like we may take unit step, we may take unit ramp, or unit parabolic, or sometimes we may take unit impulse to study the response of the system. So based on what type of input we have taken to understand the behavior of system, based on that we can calculate the value of this error signal. And then we discussed how to derive the mathematical expression to calculate the value of steady state error. So steady state error indicated by symbol ess is given by the mathematical expression like limit t tends to infinity e of t, where this e of t indicate the value of error signal but in time domain, and equation number 1 indicate the value of error signal but in frequency domain. So what we need to do here, we have applied the concept of final value theorem to convert this expression in terms of uh, frequency domain, or you can say here this entire term we have replaced by this particular expression. This is nothing but the application of your final value theorem. Limit t tends to infinity e of t, we can write this as limit s tends to 0 s into e of s. Now e of s is known to us from equation number 1. So we have replaced that by equation 1 and solve, and finally we got equation number 2, where equation number 2 indicate the expression to calculate the value of steady state error. And from equation number 2, it is very clear that the value of steady state error depends on two main factors. Number one, it depends upon the nature of input signal, that is nothing but r of s. And number two, it depends upon the nature of open loop transfer function, which is nothing but g of s into h of s. And then in the last lecture, again we discussed how to calculate the change in the error signal if you change the value of reference input signal. So we have considered some three different cases. In case one, we considered that the nature of reference input signal is unit step. Then we calculate the value of error signal like ess is nothing but 1 upon 1 plus kp, where kp is nothing but positional error coefficient, and the expression to calculate kp is limit s tends to 0 g of s into h of s. And then in case number 2, we have considered the nature of reference input signal as unit ramp function, and the value of r of s is nothing but 1 by s square, and then we calculate the value of ess, and the expression for ess is nothing but 1 upon kv, where kv is called as velocity error coefficient, and the expression to calculate kv is nothing but limit s tends to 0 s into g of s into h of s. This is very important. And then case number 3, we have taken the nature of reference input signal as unit parabolic, and then uh, based on that we have derived the expression to calculate the value of steady state error, and it is nothing but ess equals to 1 upon ka, where ka is called as acceleration error coefficient, and the mathematical expression to calculate ka is nothing but s square g of s into h of s, and we need to solve this particular expression when limit s tends to 0. This is very important. And then we discuss the concept of what is type of system. Type of system means nothing but what? It is nothing but how many number of poles are available at origin. That is nothing but type of a system. So equation number 3 indicate the general expression to calculate the open loop transfer function of a system. And here this k indicate the overall gain of the system. These brackets are responsible to calculate zeros, and these are responsible to calculate poles. And here this n indicate how many number of poles are available at origin. So this indicate poles at origin. This is very important. So type 0 means there will be no pole available at origin. Hence this is called as n equals to 0 or type 0 system. When we have type 1 system, the value of n is going to be 1. That means there will be one pole available at origin. So type of a system means how many number of poles, or you can say number of poles at origin. At origin, that is important. And then based on that, we have taken different cases to calculate the value of steady state error and positional error coefficient, velocity error coefficient, or acceleration error coefficient for different types of system. So some 9 cases we have considered simultaneously, and finally we conclude some of the most important aspect related to type 0, type 1, type 2 systems, and we club them into a final हाँ हाँ मैं शुरू किया ना, लाइव हूँ मैं भी. ठीक. So finally, we have considered all the possible cases and made this final summary from our entire discussion. And we conclude that let me check whether we are still live or not, because I'm having some technical problem at my side. Wait for a minute. Huh? Okay. So finally, we conclude that, for example, if we are dealing with type 0 system, so in case of type 0 system, the mathematical expression to calculate a steady state error when we excite that particular system with unit step input excitation is nothing but 1 upon 1 plus k. This is very important. And the moment we try to calculate the value of steady state error for type 0 system, uh, when we are dealing with unit ramp input signal or unit parabolic input signal, the value of steady state error is going to be infinite. That means type 0 system are designed only to operate on unit step input excitation. For example, if you have a type 0 system, that means if you have a system in which the number of poles available at origin are nothing but 0, or there will be no pole available at origin, then in that case, if you want to analyze the behavior of that particular system, definitely we need to take only unit step input excitation as a main input function. Then only it is possible to analyze the behavior of that particular system, because in that case only the value of steady state error is available at a minimum possible value. Apart from that, if you have a type 0 system and if you excite that particular system through unit ramp, or you can say unit parabolic, then in both the cases the value of steady state error is going to be infinite, which is not a desirable condition. So this points you have to remember. In the same way, if we are dealing with type 1, so type 1 systems are designed to operate only on unit step and unit ramp input signal. Why? Because in case of type 1 system, whenever we excite that particular system using unit step or unit ramp, the value of steady state error is either going to be 0 or it is going to be a finite value. But the moment we excite unit 1 or type 1 system using unit parabolic input excitation, the value of steady state error is going to be infinite, which is undesirable condition. So these points you have to remember. In the same way, whenever we are dealing with type 2, that means number of pole available at origin are nothing but 2, then in that case that particular system is capable to work on unit step as well as unit ramp and unit parabolic input. The thing is that in case of type 2, when we excite the system using unit step and unit ramp, the value of errors are nothing but 0. But when we excite the system using unit parabolic, the value of steady state error is going to be 1 by k, which is nothing but a finite value. This is very important. Now, one more conclusion we have drawn from this particular table, and that conclusion is that the value of steady state error is inversely proportional to overall gain of the system. That means the moment we increase the value of gain k, automatically the value of steady state error goes on reducing. This is very important. So same thing is mentioned over here, and all these points we have discussed in our previous class. This is very important. Now, in today's session, we are going to solve some numerical on steady state error and how to calculate the value of error coefficient in case of type 0, type 1, type 2 system for different types of input excitation, maybe say unit step, maybe say unit ramp, or you can say unit parabolic. So this table you have to remember. And in GATE, you may have various types of theoretical as well as numerical questions on this particular final concluding statement, like what will happen if you are dealing with type 0 system and if you excite that system through step, ramp and parabola, what will be the value of error coefficients and what will be the value of steady state error in each of the cases, that you have to remember. Now based on this, let us try to solve some numerical on steady state error calculations. So numerical number 1, this particular numerical I gave you an exam homework, and I to inform you that you have to solve this numerical. So how to solve this numerical? See, it is again simply a formula based numerical, and here the objective is uh, we have an open loop transfer function of a system like g of s into h of s is nothing but 2s square plus 3s plus 20 whole divided by s into s plus 2 and then s square plus 4s plus 10. And in this case, our objective is to determine the value of error coefficients and steady state error. That means we have to calculate the value of ESS followed by different types of error coefficients like we have to calculate the value of Kp or Kv or Ka for this particular system when this system is excited by some kind of input excitation, and different types of input signals are given to us. First one is A, which is nothing but 5, second one is 40, and third one is 40 square by 2. So how to solve this numerical? Again, first of all, to solve this numerical, we need to first identify that what is the type of this system. That means how many number of poles are available at origin. And from this equation, that means from the open loop transfer function of the system, it is very clear that here the value of capital N is nothing but 1. So this is the example of type 1 system. So this is the example of type 1 system where we have only one pole available at origin. See, the same thing is mentioned over here. It is the example of type 1 system. Now, once we conclude that this is the example for type 1 system, now what we are going to do, we will find the value of error coefficients followed by steady state error. So here we know that from the knowledge of our previous lecture, the expression to calculate Kp, which is nothing but positional error coefficient, is nothing but limit s tends to 0 g of s into h of s. So what we need to do, we know the expression for g of s into h of s, which is nothing but 2 s square plus 3s plus 20 divided by s in bracket s plus 2, again in bracket s square plus 4s plus 10. So if you solve this limit, you will get the value of Kp as infinite. And this must be a correct answer. Why? Because in the concluding statement, see, whenever we are dealing with type 1 system, the expression for Kp must be infinite. The same value we must get in the numerical, and we are also getting the same value. See, the value of Kp is nothing but infinite. This is nothing but important. Now let us try to calculate the value of steady state error. So here steady state error is nothing but 1 upon 1 plus Kp. The moment we put the value of Kp as infinite over here, the value of steady state error is going to be 0. This is very important. That means in case of type 1 system, whenever we excite that particular system by a step input, where in this particular case the value of step input, which is nothing but first case, is nothing but 5. So it is not a unit step, it is nothing but a kind of step input where the magnitude of that particular function is nothing but 5. So here this is nothing but 5. So that 5 we have taken over here. Rest of the thing is as it is. So ESS is nothing but 1 upon 1 plus Kp. So this one, when we have taken a unit step, but whenever we are having a step signal apart from unity, then in that case we need to multiply this particular signal by its corresponding magnitude. So here the magnitude of that particular signal is nothing but 5. So that's why we need to take here 5 into picture. So hence here we have taken 5. So 5 multiplied by 1 upon 1 plus Kp, but Kp is nothing but infinite. So this is going to be 0. In the same way, let's try to calculate the value of Kv, which is velocity error coefficient. And the mathematical expression to calculate Kv is nothing but limit s tends to 0, s into g of s into h of s. But we know the value of g of s into h of s. Put that value in this equation. This s and s will get cancelled out, and you have to solve this particular limit. The moment you solve this limit, you will get the value of Kp is nothing but 2. So the expression to calculate velocity error coefficient is this, and finally we got the value of velocity error coefficient is nothing but 2. This is very important. And then we can also calculate the value of ESS. So expression to calculate ESS is nothing but 1 upon kV multiplied by the slope of that particular uh, signal. So here the slope is 4. See, the in the given numerical, see, the second type of signal that we have taken to find out the steady state error followed by error coefficients is nothing but 40. So here the slope is 4. If you apply that logic, you will get the value of ESS is nothing but 1 upon kV into 4, and kV is 2. So if you calculate, you will get the value of steady state error as 2. This is very important. And the same thing we have concluded in our concluding statement, like whenever we are dealing with type 1 system, and if we excite that particular system using step or ramp input signal, here we are dealing with ramp, the value of kp is going to be k, which is in this case is nothing but 2, and the value of steady state error is going to be 1 upon kp, or sorry, kv. This is not kp, this is kv, velocity, and steady state error is nothing but 1 upon kv. So if you apply that logic, you will get the value of steady state error as well as the value of error coefficients. And then if you try to calculate the value of acceleration error coefficient, Ka is nothing but limit s tends to 0, s square into g of s into h of s. Put the value of g of s, h of s in this equation and try to solve this. Now in this case, see, this s and this s square get cancelled. If you solve this limit for s tends to 0, you will get the value of Ka as 0. And the expression to calculate steady state error in this case is going to be 1 upon Ka into its component factor. So it is going to be infinite. So finally, what we conclude that for this particular system having an open loop transfer function, g of s into h of s equals to 2 in bracket s square plus 3s plus 20 whole divided by s in bracket s plus 2 and then s square plus 4s plus 10, because it is a type 1 system, because here we have one pole available at origin. The value for acceleration error coefficient is going to be 0, and the corresponding steady state error is going to be infinite. This is very, very important. And the same thing we have made in our final table, summary table. See, whenever we are dealing with type 1 system, the value of steady state error in case of unit parabolic is going to be infinite. See, this is going to be infinite. This is very important. So ultimately, you can apply this logic directly from the table, or you can solve step by step. You will get both the answers in a proper manner. Both answers will be the same. I hope this numerical is understood by everyone. It is simply a formula based numerical where our objective is to calculate the value of Kp, Kv, Ka followed by steady state errors for a given system when it is excited by different types of input excitation signal. It may be a step, it may be a ramp, or it may be a parabolic input signal. Now let us try to solve one more numerical. The statement for this numerical is determine the positional, velocity and acceleration error coefficients for a system given below. So here our objective is to find the value of Kp, because positional error coefficient is nothing but Kp, velocity error coefficient is nothing but Kv, and acceleration error coefficient is nothing but Ka. So we have to calculate the value of Kp, Kv, Ka for a system given below. So here we have g of s, and here it is mentioned that it is a unity feedback system, hence the value of h of s is going to be 1. So if you simply take the product of forward path gain and feedback path gain, it is going to be like g of s into h of s. It is going to be like k whole divided by s in bracket s square plus twice zeta omega ns plus omega n square. That's it. And second is open loop transfer function of the system is g of s into h of s equals to 100 in bracket s plus 2 s plus 40 whole divided by s cube in bracket s square plus 4s plus 200. And here our objective is to find the value of kp, kv and ka. That's it. Now for case number 1, the moment we have numerical to calculate the value of error coefficients or to calculate the value of steady state error, the very first step that we need to implement is we need to identify that what is the type of given system. That means how many number of poles are available at origin. For example, if you take first system, here we have one pole at origin. That means the value of n in this case is nothing but 1. So this is the example of type 1 system. This is very important. In the same way, if you see the open loop transfer function for case number 2, see here we have s cube. That means we have 3 poles at origin. Hence, in this case, the type of system is 3, or it is the example of type 3 system. So, the very first step that we need to implement in order to solve numerical on either error coefficient calculation or steady state error calculation, the very first step is we need to find the type of system. What is the type of that system, whether it is type 0, 1, 2, 3 or so on. And then once we have decided that for case 1 the type of system is 1, then we straight away use our formulas to calculate the value of kp. How to use kp or how to find kp? Kp is nothing but limit s tends to 0 g of s into h of s, where g of s h of s is given to us. Put the value of g of s h of s in the expression for kp, solve for s tends to 0, you will get the answer for kp. In the same way, to calculate kv, we need to use a formula like kv is nothing but limit s tends to 0, s into g of s into h of s. In the same way, for ka, we have to use a formula like limit s tends to 0, s square g of s into h of s. That's it. So if you apply that logic, we can calculate the value of kp. So kp in this case is limit s tends to 0 g of s into h of s, but in this case because it is a unity feedback system, hence the value of h of s is going to be 1, so no need to multiply it by h of s, so you will get the answer as infinite. In the same way, if you try to calculate kv, it will be like limit s tends to 0 s into g of s into h of s. And here in this case this s and s will get cancelled and you will get the value of this kv as k upon omega n square. In the same way, if you try to calculate the value of ka, that is nothing but acceleration error coefficient, so it is going to be like limit s tends to 0 s square g of s into h of s, and here this s square and this one s can cancelled, so here we have only s in the numerator, and if you try to solve this expression when s tends to 0, you will get the value of ka as 0. That's it. I hope this point is clear to everyone. Please take your time, note down these points. This is very important. If you are done with this, now let us try to calculate for the second system which is given to us in the numerical. Again, our objective is to find the value of Kp, Kv and Ka. But in this case, the type of system is 3. That is important because we have 3 number of poles available at origin. And again apply the same formula. Kp is limit s tends to 0, g of s into h of s. And this is what g of s into h of s is. So if you solve this limit as s tends to 0, the moment you put s equals to 0 over here, this is going to be infinite. This is very important. In the same way, if you try to calculate the value of kv, it is s limit s tends to 0, s into g of s into h of s. So this s, and here we have a square in the denominator. And the moment you solve this for s tends to 0, you will get again infinite. And if you try to solve for ka, it is like s tends to 0, s square g of s into h of s. So this s square and this cube will get cancelled. Here we have only s in the denominator. And the moment you solve this for s tends to 0, again you will get the value of acceleration error coefficient as infinite. So what we conclude, that for higher type system, that means a type of system above 2, it may be 3 or it may be 4 or it may be 5 or say it may be up to infinite, the value of error coefficients, it may be positional, it may be velocity or it may be acceleration, they are always going to be infinite. See, in all the 3 cases we got the value of error coefficients as infinite. That is important. Please note down this. Now let us try to solve this numerical. In this numerical, the statement is the closed loop transfer function of a unity feedback control system is given below. So C of s by R of s is nothing but Ks plus beta whole divided by s square As plus beta. And here our objective is to determine the value of steady state error for a unit ramp input. So here closed loop transfer function is given to us for a unity feedback control system. Okay, and our objective is to determine the value of steady state error. That means we need to calculate the value of ESS. Also, yeah, we have to calculate the value of ESS for a unit ramp input signal. That means when the value of R of S is going to be unit ramp. So in case of unit ramp, it is going to be 1 by S square. I hope this is clear to everyone. For unit step, it is 1 by S. For unit parabola, it will be 1 by S cube. And for unit impulse, it will be 1. So in this case, the value of input signal is unit ramp. That's why the value of R of S is going to be 1 by S square. And in this case, we need to find the value of what? Steady state error. So how to solve this? You can reply in the chat box also if you have any idea to solve this numerical. Think it is very simple numerical where our objective is to find the value of steady state error for a system whose closed loop transfer function is given to us, that to a unity feedback control system, h of s is nothing but 1, and it is excited by a unit ramp input. Okay, let us try to solve this. So for a unity feedback control system, closed loop transfer function is given by C of s by R of s is nothing but G of s upon 1 plus G of s into H of s. Now why we have written this expression? Because it is a unity feedback control system. That's why the value of H of s is going to be 1. So no need to write H of s over here. Now what we need to do, we have to compare this with the given closed loop transfer function. So given closed loop transfer function is ks plus beta whole divided by s square plus as plus beta, and this is going to be equals to g of s upon 1 plus g of s. And now we need to solve this for g of s. So if you solve this for g of s, you will get g of s is nothing but ks plus beta whole divided by s square plus s in bracket alpha minus k. This is very important. And the moment we have the expression for g of s, now it is very easy for us to find the value of steady state error. First we calculate the value of error signal, and then we can apply that logic to calculate the value of what? Steady state error. That's it. So we know that es or e of s is nothing but r of s upon 1 plus g of s into h of s. This we have already derived in our previous class. Now since it is a unity feedback system, the value of h of s is nothing but 1. So we can write this as e of s by r of s is nothing but 1 upon 1 plus g of s. Or we can solve this by substituting the value of g of s, which we have calculated previously, in this equation. That's it. So the moment you put the value of g of s over here, and if you try to calculate for this, you will get the expression for error signal as e of s is equals to r of s multiplied by this entire term. Now in the numerical, it is given that we need to calculate the value of steady state error when the system is excited by unit ramp input signal. And I told you that for unit ramp input signal, the value of r of s is going to be 1 by s square. I hope this point is clear to everyone. So what we need to do? We need to put the value of r of s as 1 by s square and try to solve this particular numerical to calculate the value of ESS, which is nothing but steady state error. So I can write steady state error as limit s tends to 0 s into E of s. Now here E of s is nothing but this entire expression, and in that expression we need to replace this r of s by 1 by s square. That is important. So what we need to do, this has to be multiplied by 1 by s square, because this r of s is nothing but 1 by s square. So this s and this s square get cancelled. So here we have s in the denominator, and here this 1 upon s into entire structure we need to put over here. So if you solve this, you will get this as an output. So here E of s is nothing but 1 by s square into s. So this s square, this s will get cancelled. So ultimately we need to solve this expression only, where limit s tends to 0. So if you solve this, you will get the value of steady state error as alpha minus k upon beta. This is very important, and this is our final answer. I hope this is clear to everyone. It is simply the application of limits and all. That's it. It is simply the application of mathematics. If you know the formula to calculate the value of error signals for different types of input which we have taken as an excitation to excite that particular system, you can easily find out the value of error signal. You can easily find out the value of error coefficients for any type of system. The thing is that you need to first identify what will be the type of that system. It may be type 0, type 1, type 2, type 3, and so on, and then apply proper logic. Think twice before applying a logic to calculate the value of error coefficient followed by steady state error. Once you have decided, apply that logic and get the answers. The thing is that you need to solve only limits. That's it. Limit s tends to 0 for different types of conditions. So the theory And the numerical on this topic is very simple. The thing is that if you have the knowledge of what exactly error coefficients are, how we can calculate error coefficients for different types of system, for different type of input signal, apply that logic, you will get answers within a fraction of second. That's it. Or I can say that these are directly formula based numerical. If you have done with this, now let us try to understand what are the different steps that we need to implement in order to find the time response analysis of a control system. So there are some steps that we need to follow in order to find the time response analysis of a system. So first step that we need to implement is determine the overall transfer function of a system. And then step number 2, determine the response of a system in frequency domain. That means calculate the value of C of S by identifying the type of reference input signal. So step number 1, find out overall transfer function, which is C of S by R of S. Then step number 2, determine the response of a system in frequency domain, that is C of S, by identifying the type of reference input signal. That means identify the value of R of S, whether it is for step, ramp, parabolic or impulse, and try to find out the value of what? C of S. And then in step number 3, apply inverse Laplace transform to determine the value of C of t. That's it. Where C of t is nothing but Laplace inverse of C of S. And then the steady state value of system we can determine, because we know that, and I told you that the total response C of t is nothing but a combination of transient followed by steady state. So by applying that particular logic, we can easily find out the value of CSS, where CSS indicate the steady state response of the system. And this is nothing but when t tends to infinite, whatever the value of C of t available with us, that indicate the CSS. And if you know the value of CSS, we already calculated the value of C of t, we can easily find out the value of CT of t. So CT of t is nothing but C of t minus this entire term. That's it. See, the same thing is mentioned over here. So these are the simple steps that we need to follow in order to find time response analysis of any control system. First, obtain overall transfer function. Then determine the response of a system in frequency domain. Then apply inverse Laplace to find the response in time domain. And once we know the total time response in time domain, determine the value of that response at t tends to infinite. That component indicate the steady state value. Once you know the total value, once you know the steady state value, subtract that value from total, you will get transient response. That's it. So CT of t is going to be C of t minus CSS of t. That's it. Now, let us try to calculate the time response of first order control system. Now, what is order? Order means the highest power of S available in the denominator polynomial function that indicate the order of a control system. So, see here, the order of a control system is decided from the highest power of S available in the denominator polynomial function of the transfer function. That is important. Or order is nothing but how many number of poles are associated with that particular system. In case of first order system, the highest power of S in the denominator polynomial function is always equals to 1. That means that particular system have only one pole. It may possible that that pole is available at origin, or it may possible that the pole is available at any other complex frequency. The thing is that that particular system has only one pole. That means the order of that particular system is 1. That is important. So the block diagram for first order control system is given like this. So this is the example for first order control system. Now, why it is the example for first order control system? Because if you apply block diagram reduction technique or elimination of closed loop over here, and if you try to calculate the transfer function for this system, if you compare the denominator polynomial function of that system, you will find that there will be only one value of s available in the denominator. That means the highest power of s available in the denominator polynomial function of this particular system is 1. That's why you will get this particular system as first order control system. And one thing is very interesting over here. Again, we have taken a negative feedback system over here. So here it is a unity feedback control system, that too first order type. The value of h of s in this case is nothing but 1. The value of g of s in this case is nothing but 1 upon s into capital T. Now, if you try to find the transfer function for the system, it will be like C of s by R of s is going to be 1 upon st plus 1. This is very important. Now, from where we got this? Apply block diagram reduction technique, or straight away apply elimination of closed loop. You will get this answer. That expression is g of s upon 1 plus g of s into h of s. Now, in this case, g of s is 1 upon st, and h of s is nothing but 1. Put that value, solve this, you will get this as an answer. Now, from this transfer function, it is very clear that, see, the highest power of s available in the denominator is 1. See, here we have s to the power 1. That's why this is first order control system. I hope this point is clear to everyone. Order means highest power of s available in the denominator polynomial function, or how many number of poles are associated with that particular system. If it is first order, that means only one pole. If it is second order, that means two pole are associated with that particular system. That's it. So if you are done with this, now let us try to find out the response of this particular system when it is subjected to a unit step input function. So the moment we take unit step, the value of R of s is going to be 1 by s. I hope this is clear to everyone. So apply those logic one by one. If you are interested to calculate the value of time response for any system, what we need to do? First, we need to calculate the value of transfer function. So that we have done. Then we need to decide what type of input we have taken as an excitation. So in this case, we have taken the input as unit step. Hence, the value of R of s is going to be 1. And then we are trying to calculate the value of response in frequency domain. And then we are calculating the value of C of t by taking Laplace inverse. That's it. So output is 1 upon s into 1 upon st plus 1. So this indicates the output of the system, but in frequency domain. Now apply partial fraction technique to convert this into some standard form, because ultimately we want the response in time domain, and the moment we want response in time domain, we need to take Laplace inverse of C of s. So what we are going to do, we will convert this into some standard form so that we can apply some standard Laplace inverse topology to get their answers into final version. Hence, we are applying partial fraction technique. And if you apply partial fraction technique, you will get the value of a as 1 and b as minus t. Put them over here. So this will be the response of a system, but in frequency domain. So this is, I think, our step number 3. Let me check whether it is step number 3 or step number 4. It is step number 2. In step number 1, see, we have to calculate overall transfer function. And in step number 2, we have to calculate C of s in frequency domain, that we have done. And now we need to apply inverse Laplace to find out C of t. That means a response in time domain. So by taking Laplace inverse on both sides, we can calculate the value of C of t. So this C of t indicate the time response of that system, which is 1 minus e to the power minus t by capital T. Let this will be your equation number 2. This is very important. Now, suppose if you are interested to calculate the value of steady state response. So how to calculate steady state response? It will be like limit t tends to infinity C of t. And the moment you solve this for limit t tends to infinity, it will be 1. Why? Because see, the moment you put the value of t tends to infinity, e to the power minus infinity, this is going to be what? 0. So 1 minus 0, this is going to be 1. That means finally the response of the system will achieve a value of 1. See, this is 1. So CSS will be 1. Now C of t will be 1 minus e to the power minus t by capital T. So if you are interested to find transient response, it will be simply CSS of t minus C of t. So it will be this. So we conclude that the steady state response of the system is 1 and the transient response of the system is e to the power minus t by capital T. And the total response is 1 minus e to the power minus t by capital T. And from this, it is very clear that the moment we increase the value of t, automatically this particular function is deteriorating. That means, see, the expression for steady transient response is e to the power minus t by capital T. At t equals to 0, this is going to be like e to the power 0, which is nothing but 1. And the moment you increase the value of this, e to the power, say, minus 1, minus 2, minus 3, or if you put t as infinity, e to the power minus infinity, this term is going to be 0. That means it is gradually goes on reducing. That means the transient response is dying out and the response of the system is reaching towards its actual value, which is nothing but 1. Hence the system is absolutely stable. That is important. I hope this point is clear to everyone. So if you apply that logic, we can write this like C of t is nothing but 1 minus e to the power minus t by t. That is very important. Now let us try to understand what exactly the meaning of time constant. This is one of the most important terminology that plays an important role in case of time response analysis of a system. So what is time constant? Time constant means what? It is the time taken by the response of a system to reach 63.2% of its final value in first attempt. That is called as time constant. Now why this is 63.2%? Why not any other value? That we are going to learn over here. Now see here, in this case, let us consider that this capital T is nothing but a time constant, and we are trying to find out the response of this particular system at one time constant. That means what we need to do, we need to replace this small t by capital T. And let us try to calculate what will be the value of this C of t over here. So if you put t equals to capital T and try to solve, you will get the answer of C of t as 0.6321. Or if you try to calculate this in terms of percentage, you will get 63.21. Hence, time constant is defined as the time taken by the response of a system to reach 63.2% of its final value. This is very important. I hope this point is clear to everyone. Now, this is what the variation of output with respect to time. And here at one time constant, the response reaches to 63.2% of its final value. Final value is 1. So 1 का 63.2% कितना रहेगा? 0.6321. In the same way, Suppose if you are interested to calculate the value of response at 2 time constant, see, it is equals to 86.5% or 0.865. In the same way, if you are interested to calculate the value of response at 3 time constant, it is close to 95%. See, over here, that is 0.95. In the same way, at 4 time constant, the response is close to 100. It is 98.2%. So somewhere over here, like this. So this is going to be like 0.982. In the same way, at pi time constant, the response is almost 100, but not exactly 100, because I told you that when you put t equals to infinite, then only this is going to be your 0, and the value of c of t is going to be css of t, that is going to be 1. So at pi time constant, the response of the system reached to almost 100, which is 99.3%. That is important. And from this, it is very clear that whenever you have a system, and suppose if you're interested to find out the steady state response of the system, or suppose if you're interested to find out the transient response of the system, normally we study the response of that particular system for 4 time constant, or you can say 5 time constant, because after that the response is almost reached to 100 value, or 100%, not exactly 100 but very close to 100. This is very important, and this is what the importance of time constant. So same thing is mentioned over here. See, at 1t the response is 63.21 of its final value. At 4t the response is almost reaches to 98% of its final value. See, that is important. Now let us try to understand what is the effect of time constant on the response of control system. Now see here, what is time constant? It is the time taken by the response of a system to reach 63.2% of its final value. The moment we increase the value of time constant, that means the time taken by the response of the system to reach 63.2% is also goes on increasing. For example, if time constant of some system is say 1 second, that means in 1 second the response of that system will reach 63.2% of its value. In other case, suppose we have a system where the time constant is 10 seconds. That means that system will take 10 seconds to reach 63.2% of its final value. So what is the impact of changing time constant on the response of the system? The moment we increase the value of time constant, the response of the system become sluggish. वो धीरे धीरे करके उसके फाइनल वैल्यू तक पहुंचेगा. जितना टाइम कांस्टेंट आपका कम रहेगा, उतना सिस्टम का रिस्पॉन्स फास्ट रहेगा. Are you getting my point? So same thing is mentioned over here. See, this is very important. The decrease in the value of time constant indicate that the steady state reaches earlier. This is very important. Therefore, lower the time constant, faster will be the response of the system. See, here I have shown the responses of two systems on the same graph. First one is corresponding to T1 and second one is corresponding to T2. And in this case, the value of T1 is you can say less than T2. This is very important. See, because of that, the response of first system is quick and fast as compared to the response of second system. This is very important. Now we will take a break of half an hour, and we will continue with our sessions with the next link. Thank you.